All right. Announcements. We have an assignment due Wednesday. Get it in sooner if you can. We have an exam Friday. We will review for that on Thursday. There's a study guide on Canvas you should be looking through. Please do come prepared on Thursday with as many questions as you possibly can. I will not have quite as much prepared for this exam as I did historically, or I guess I did on the first exam. I had some practice problems ready to go. I have that for exams 1 and 3, but not for 2. So I'm going to rely on people coming in with questions. If you want me to prepare anything like we had for exam 1, send me that information well in advance, at least 24 hours in advance. I will do what I can to have something ready to go over or some practice problems for them. Otherwise, I will be relying on you all. Otherwise, I will stare awkwardly at you and wonder what we are doing here. It'll be a grand time. Questions before we dive in? Back into Turing machines. Excellent. Off the deep end we go. All right, last time we got a couple more examples of Turing machine programs. We ended up looking at A to the n, B to the n, and then A to the n, B to the n, C to the n, and determining that we could recognize languages that weren't context-free. And so what I had said from the beginning, we have evidence of now of being able to map Turing machines to languages that represent that of any program that we could write for a programming language, which is pretty cool and also kind of scary. So last thing we'll do is go ahead and write a transducer program. So transducers turn input into output, where the output that is on the tape is relevant and valuable. It's not just scratch space before we accept or reject. Now we are going to add 2 unary numbers. So this is not binary, it is unary. The only digit in these numbers is 1. And there are as many 1s on the tape as there are like tally marks. There are as many 1s on the tape as there are digits in the number. And there is also going to be a plus symbol on the tape. So we're going to assume that what we have is something like 111 plus 11. And the goal after to finish that would be 11111, where we have just those 5 1s and nothing else on the tape.
And either of these be 0. Right, positive.
Instead of a plus, you could imagine there also being a 0, where the 0 representing the space between the numbers. Doesn't really matter what the separator character is. You can choose whatever separator character you want, as long as it is not a blank. Here I say that the separator character is a 0, but you can imagine it being a plus. You can imagine it being really any other separator character you want. But yeah, 2 unary numbers. And the goal is when the tape terminates, what's on the tape, or when the program terminates, what's on the tape is a unary number that is the answer and nothing else. How are we doing? People feel like they know how to start or know how to think about it? Yeah,
Just take the leftmost side down to the rightmost side until.
that's making an assumption about what's on the right-hand side. But yes, that certainly could work. I think it's easier to append from the right-hand side, because then you're verifying as you go that it's in the associated form that you want, but you easily could append from the left-hand side and then validate the right-hand side is what you expect. Yeah, this isn't anywhere near as hard as you might think. We have some answers. Anyone still working and wants a little bit more time? Take a little bit more time.
When we're writing these programs, because we're doing just the transitions, should we just be stating beforehand, like, this is the initial state, these are the final states?
Yeah, whenever you write a Turing machine program, just like any other, you would actually write it as that 5 tuple and the associated transitions. And that 5 tuple, I guess in this case, it's a 7 tuple, but it states which of the states is the starting state, what set of states are the terminating states. Right, let's see if you have an answer that looks like this. Starting at the beginning, we're going to go over all of the first numbers ones. When we see the first 0 or any 0, we are going to convert it into a 1 and switch states. This says we've seen the 1 0 or the 1 separator character that we are going to see, so that if we see another 1, we're no longer in Q0. We are expecting just 1 separator character. Then we continue going past all of the 1s until we see a blank. When we go past that, when we see that blank, I agree with that. We're going to go back left. We can just turn that blank into a 1 and call it a day. No, we need to go back to that last 1 and turn it into either a blank, or I guess in this case, it's trying to turn it into a 0.
I was trying to do like.
Yeah, it makes just the most sense to me to turn that into a blank and call it a day. So with this program, I think what it's trying to state is that we want to terminate the program with the output where the read-write head is ready to read the output. So it has to be at the farthest left character in order to do that. So turning the 0 into a blank, I think, or the last 1 into a blank is more representative there. And then if you needed to go back to the very beginning, you could do that. So the only change I would make is in this transition, turning this into a blank. And then you could go back left over everything and stop at the far left and say, what's to the right of this is the output. Questions on this solution? How do we feel about writing the transducer? That's about as easy as transducers get, but In general, Turing machine programs are just complicated, frequently unnecessarily complicated, or seem and look unnecessarily complicated for us humans to look at and design. So we're going to transition a bit from playing the programmer's role with Turing machines to playing the analyst's role. We're going to look at what modifications we can make to Turing machines without affecting their computational power in ways that might make life easier on us, the human, so that we have a little bit more to play with, rather than just this base Turing machine. So to do this, we're going to look back a little bit at some of the theory. And Turing machines, of course, come from who might be considered one of the founding fathers of computer science, Alan Turing. I can't talk about this guy enough. He was an absolute genius. So he wrote his thesis on Turing machines and said that they're capable of any computation that a modern mechanical computer is. The question that I would have for people is, how could we actually show that? How could we prove this concept that any program that we could write on a mechanical computer, we could write on some kind of Turing machine? We need some kind of emulation to be able to show that whatever we could do, we can do on a Turing machine. Any thoughts on how you would go about that proof? Yeah.
Show that it can emulate the individual components of or at least the digital aspect of a computer.
Okay.
Basically like unit testing.
Okay. You could certainly take a unit testing type of approach. Any other thoughts? It turns out that, yeah, go ahead.
My first thought is kind of like, almost something like, I don't see how this can make sense, but almost something like inductive in the sense that like, if they can effectively solve this, then it's implied that it can also solve everything else.
Okay, some kind of inductive
Yeah.
hypothesis where we build up the absolute basic bare bones. Here is what the basic proof types are. All logic is built on these foundational blocks. So prove that it can do these foundational blocks, and then everything else would follow.
Yeah, something like, I don't know how that would look, but that's.
Yeah, that's kind of how math is built, right? You prove that 1 is the successor of 0, 1 plus 1 is 2, and then kind of all math snowballs from there. The unit testing approach tends to be very bloated and prone to error. So while it was considered, we mostly had to take a more theoretical approach to it because it is incredibly difficult to show, even for simple programs. But we want to be able to, in some capacity, move from using a basic Turing machine to high-level pseudocode, high-level block diagrams, high-level code ideas. So we can start, since we've shown that Turing machines can recognize languages that are more complicated than push-down automata can represent. But we'll start with that assertion and try to work from there in ways that can we generate other kinds of Turing machines that are equivalent in their associated language classes. So let's start with a discussion on the equivalence of automata classes. We can state that 2 automata are equally powerful or equivalent. I guess they're equivalent in general if they accept the same language. They're equally powerful if the construction of that class of automata can accept the same set of languages. So the DFA and NFA was one class. The deterministic pushdown automata was another class. The non-deterministic pushdown automata was another class. And we found that 2 of these classes were equivalent if, given that we could make an automaton in the first class we could make an automaton in the second class that could accept the same language for every language in that class. Similarly, we also need to be able to show that for every automaton in the second class, we can build an automaton in the first class that accepts the same language. We showed this with converting NFAs into DFAs. For any given NFA, there's an associated DFA. And it's pretty trivial to say that for any DFA, there is an equivalent NFA because it's already a restricted NFA. So there is no reason to even consider that question. But we could show that they were the same class basically by just showing that for every NFA that you can construct, there is an equivalent DFA. But we can do exactly the same thing for Turing machines and for different ways that we could modify Turing machines. So what we can do is we're going to build a Turing machine that simulates the moves of another Turing machine as a way of emulating this idea. Can we take the base Turing machine, take some feature that we would like to add to that Turing machine, and somehow show that given the first Turing machine, we could simulate the second Turing machine, and with the second Turing machine, we could simulate the first Turing machine. If we could do that for every class of languages that a Turing machine could accept, then we would be able to show that these different classes of Turing machines are equivalent. So, what are some things that we would like to be able to add to Turing machines? We can start brainstorming functionality that would make our lives as the programmer a little bit easier. A stack. We're going to start even simpler than that. It's annoying that we have to move left or right every time that we transition. So what if we could just say, let's not. Let's just decide, you know what, the read-write head is not moving this time. Could we go prove and show that a Turing machine with the ability to move left or right or stay is equivalent to a Turing machine that just moves left or right? We talked about this ever so briefly a couple class periods ago, but we're going to start adding functionality to our Turing machines and seeing if we can break this concept of equivalence. Like how much power can we add to the Turing machine without really changing the class of languages that it can accept? So, possible moves of a Turing machine with a stay option are now left, right, and stay. You can imagine now if I asked you the question, does this increase the power of a Turing machine? Is there some kind of language that we could represent with a machine that could move left or right or stay that we could not represent with just left and right? If the answer to that is no, then how would we simulate a stay with a Turing machine that could just move left or right?
You can just, whatever input that you want to stay on, you just move to the right, and then whatever it is, you just move back to the left.
Yeah, so you'd have to have a set of possible transitions for everywhere that you could be, that whenever you read that character, you also write that character and then move back the direction you came from. So given that you moved right, read the character, write that same character, move back left. If you move left, read that character, write that character, and move back right. And that would simulate or emulate a stay. So it takes two transitions in one Turing machine for what another Turing machine could do in one transition, but you could map any instruction set of one Turing machine onto the other, and you would have two machines that are capable of doing the same thing, it's just with slightly different instruction sets. So the answer is no. This does not increase the power of a Turing machine. If you are curious about the exact proof of how to show this, the textbook does a great job for that. Given that it's an undergraduate level course, I find that intuition is the best way to describe things. But again, math professors would probably have my head for that. Let's think about some other things that we might want to do. Isn't it really annoying that we only have a single tape? What if we wanted to duplicate that tape a bunch of times and have different tracks? So there'd be something on track 1, something on track 2, something on track 3, something on track 4. maybe there's input here, scratch tape here, output here, and we move the read-write head together across the 3 different tracks. Maybe we don't want 3 tracks, we want 10 tracks. But the read-write head is kind of an array now that looks at the value at the current cell and can move left, 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 right, 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 etc., but in tandem like that. So we would have something that looks kind of like this. The question I have for you is this more powerful than a simple Turing machine with a single tape? Can this recognize a language that a simple Turing machine could not recognize? If so, what are the ideas of the languages you think that would look like? If not, what's your argument?
You just have a simple Turing machine with strings instead of symbols. Treat it the same way.
What do you mean by strings?
Like each cell on the tape could just have 3 symbols.
Okay, so having 3 symbols on each track, or you could even go track 1, position 1, track 2, position 1, track 3, position 1, track 1, position 2, 2, 2, etc. And then write a program that reads them in sequence rather than reading them all together. Smart. Yeah, that's exactly right. So the answer is no. This is not more powerful than a simple Turing machine. And what's great about going over these is after showing this or being able to reason through why it's not more powerful, you can start writing Turing machines with these augmented, or Turing machine programs with these augmented Turing machines. There is nothing that says now we can't write a Turing machine program on multiple tracks and make a multiple track Turing machine program. We could imagine restricting the tape to be unbounded, but only in one direction. So now instead of an infinite tape in both directions, there is a first cell, index 0. It extends forever in one direction, but only in one direction. This is what the band actually meant when they named themselves.
You're talking about Turing machines.
Yes.
It'll strike me as
One direction.
be a big judgment.
What do we think? Is this less powerful than a simple Turing machine? Does this restrict a Turing machine in a meaningful way?
Because you still have infinite data. You can, like, if you need more space, you can just keep going to the right in this case. I can see it being more annoying, but I don't see it necessarily restricting it.
Yeah, you can imagine a language or some kind of input where you read it and you really want to operate based on something, but you want to operate and extend in that direction, but you really could just map that direction onto the end of the right direction as well and flip it. And you would be able to map that instruction set, that transition set onto the Turing machine. So again, the answer is no. It is not significantly, it's not at all less powerful. It might become a little bit more annoying to write the program for it, but it's not actually less powerful. Let's keep going. Extra types and extra read-write heads. So now instead of forcing the read-write heads to move in tandem, we have separate read-write heads where one can move left, the other can move right. So multiple tapes and multiple read-write heads that don't move together, they move independently. Is this more powerful than a simple Turing machine?
Again, no, because it's like the 3 set of tapes. Now you just, instead of having to go from one set, then go over to your other data set and come back, you can just have those both open at the same time. Like,
Interesting. How are you simulating this on a standard Turing machine?
You need a ton of different states. so that you can move back and forth between the two tapes on one tape. But use states to basically memorize like where the other tape is. That makes sense.
Yeah. Yeah, that's pretty close. You would interweave them again, but whenever you would move right with the first one, you would move, if there were only two tapes, you'd move right twice, and that would get you to the next iteration of tape one. And then you would go back to a position on tape two and make a decision from there, and you would have to store the associated where to move based on each, storing a particular location, writing that to another location on the tape. So it's kind of like method calls where you hop around between the, it is disgusting. The proof is actually really gnarly. But again, the answer is no, that it is not more powerful. Eventually I will mess with you, and the answer will be yes. Maybe.
The second I started speaking, I was like, wait a second, is this the one time?
It's
Yeah.
challenging to think about at times, because you'd actually have to go through and prove that for any program you could write with this kind of Turing machine, you could emulate that on a simple Turing machine, which mapping those instructions is very difficult.
One of these is gonna be like, can we unencrypt the blockchain in all of real time?
A lot of this actually, and the reason I don't go into this is it steps on the toes of a future lecture as to how to think about this. And maybe if there's time or interest, if people remember this, we can go back to these slides and talk about how that concept can be used to help prove this. Next one, adding an extra dimension to the Turing machine. So now instead of moving left, right, or left, right, and stay, we're going to move left, right, up, or down in an infinite matrix.
So you basically have, there's an evil. So I guess it's kind of how 2D arrays are stored in C, right? So they're actually just one after another.
The issue there is when you define it at runtime, you're defining the length of the array.
You have to.
So that tells you the math you need to be able to index a cell in a later row. If those rows are infinite in size, is there a way to do that?
I mean, you know that there is infinite space in like the one-dimensional tape, but then the only thing I'm thinking of is like your row, the second you run out of space, then you have to go get it from someplace else, which then means you have to have a set of states that's like, oh no, this is an edge case, go grab more information, which I don't know.
Can't you take?
If having multiple write heads and multiple tapes doesn't make it any more powerful, I would say this would also not make it more powerful because each row is can be treated like a separate tape.
Interesting. Interesting.
The way that languages do that now is by just expanding them on the fly, right? Like a listed job.
Mhm. My question for you is, so the answer to this is no. You are right. Thoughts?
Seems like it could just kind of be done sequential. You could, every row that's going up could just be another add-on.
We don't want to do this row-wise.
Or maybe
Just-
every column could be turned, could be added to the main tape.
Even every column is infinite in nature, or is infinite in size, so we need some other way to navigate this space. Turns out that you want to spiral from cell 1, 1.
That'd be so hard.
And then you map that onto a one-dimensional tape, and then you can use math to figure out, based on the row cell combination, that will map to an element of the one-dimensional tape.
So then you can do 3D arrays too.
3D arrays, 4D arrays, the number of dimensions here don't matter. There's always a path and a function. And well, actually, this is part of what I am hinting at for later, is ways to navigate spaces intelligently. But yeah. So the answer so far has not been yes. We can make a bunch of changes to associated Turing machines without changing their associated complexity, as long as we have an intelligent way of converting between one and the other. Questions on any of these, or why that works?
I'd really like to know why the spiral works on the 2D. That's. It doesn't make any sense.
it turns into a function. You see 1 and 1, we're gonna map that to 0. We're going to see 1 and 2. And we find some way of mapping this XY pair onto an integer. What is that function? There should be something times the first number plus the second number, or something like that, some kind of linear combination, some kind of quadratic combination, something that turns this pair into a unique integer.
Something.
So coming up with that function would allow you to analyze based on the row column pair which cell on the one-dimensional tape you would store it at.
It's like Cartesian to canonical.
Yep.
Like,
And remember that this can be negative as well, because this is positive and negative in both directions on a standard Turing machine. So you can map it onto the negative integers as well. You just can't ever have duplicates. You can't have two cells that map onto the same integer. So fun at home project for when you're bored, having trouble falling asleep. Try to find that function.
And the function couldn't map a gap either, right? You would have to be one,
It could, there could be gaps.
it could gap.
Yep. As long as there is a unique integer for each. So there's not one solution to this, there are many solutions to this. There are infinite solutions to this, but there are also infinite non-solutions to this.
it's infinite wrong answers.
Something we haven't discussed, non-determinism in Turing machines. So now the question I will ask is, nothing that we've done so far has changed computational power, but what about non-determinism? Does non-determinism in a Turing machine affect the power of a Turing machine?
Well, we're like talking about like you being able to do anything that a modern computer could do on a Turing machine. Since we have non-deterministic concepts of what modern computers could do, then probably.
Could you always write a non-deterministic algorithm for a deterministic algorithm? And vice versa. If I give you a non-deterministic algorithm, could you convert it into a deterministic algorithm? We don't care about efficiency at this point. We just care about, is it possible to turn a non-deterministic machine into a deterministic machine with some
I mean,
process?
that's why we have the equation P equals NP, right?
That would be saying that what we can do in non-deterministically in polynomial time, we can do deterministically in polynomial time, but we don't have a proof for that.
Got it.
So now we're taking into account the efficiency of the associated algorithms.
Understood.
If we don't care about efficiency, so efficiency is the big problem with non-determinism for sure. So parallel choice is not mechanical. So we need some way of determining whether non-determinism adds power. So what we know about non-determinism, if any thread leads to acceptance, then we accept. So we turn kind of a parallelized algorithm into a search. There's no bounds to the breadth of that search, but we do know we don't allow for infinite parallelism at any one step. There has to be a finite branching factor. And even if that leads to an absolutely massive problem, it's still something that can be searched via breadth first search, depth first search, frills to those like iterative deepening, bidirectional search. But let's say the deterministic Turing machine will keep track of all possible non-deterministic states on its tape. Whenever we branch or fork in the non-deterministic version, the deterministic version is going to keep track of and add to some kind of data structure, which we know we can represent, like a stack or a queue. All of the exploration that we need to do in that search space. So if we're password cracking and we can fork into 62 possible branches for the first character, we would add to the queue 62 first characters to go explore. Then we'll pull out of that queue an A, and then we will branch from there, and we'll explore all of those. So it turns a non-deterministic program into a deterministic one. So deterministic Turing machine looks at all active configurations of the non-deterministic Turing machine and updates them according to the program of the non-deterministic Turing machine. That's a more complicated way of saying exactly that same thing, but again, just using what a Turing machine can do. And if we continue down that road, we can conclude that we can convert between non-deterministic Turing machines and deterministic Turing machines. And that's a little crazy to think about. For every deterministic algorithm, there is a non-deterministic algorithm. For every non-deterministic algorithm, there is a deterministic algorithm. So we can convert between the two. It's just at what cost? So this is a very fascinating theoretical result that says if we had infinite compute power, we would be able to handle non-deterministic, we would be able to write and parse non-deterministic algorithms. It's just that we don't have infinite compute power. And in fact, some non-deterministic programs are so efficient that the deterministic version of that is so inefficient that with the modern power we have, there's no way that that algorithm would finish before the Earth is enveloped by the sun. So by the time humanity is extinct, we still won't have an answer to that problem. But theoretically, the algorithm would finish at some point. We would be able to answer anything at any scale that non-determinism can ask.
Last answer 5.
That's not necessarily non-deterministic. That may just go on forever and never repeat. But we don't know. In fact, what we'll talk about later is the answer to that question may be unanswerable. That we may never know. And in fact, there are other problems that we may never know the answer to. And there are some really interesting versions of those. Like, are we familiar with the twin primes conjecture? That says that, for instance, 3 and 5 are primes that are separated by 2. We go a little ways down the number line, and 17 and 19 are primes that are 2 away from each other. It turns out that as far as we can check, there are primes that continue to be generated that are 2 away from each other. That includes primes that are thousands of digits, millions of digits. There are still primes that are 2 away from each other. Does that ever stop? Or is there a pattern to the associated twin primes? We don't know.
So does this, but this doesn't mean that it adjusts the scope of what kind of languages the Turing machines.
Correct.
Yeah.
Yeah, Turing machines can do deterministic and non-deterministic work. It's just a matter of the associated efficiency. So we're going to define this really cool idea called a universal Turing machine. And this addresses the difference between everything we've talked about so far and the modern computer. And it's that the modern computer can be reprogrammed. We can write a new program in the old program's place and run that. So what could we do to design a Turing machine such that we could reprogram it? Like our CPUs, we feed in a new program and that CPU runs that new program. With a Turing machine, we have a particular state machine and that defines the algorithm that this Turing machine runs. We would have to swap out the associated state machine to be able to do that. So what we need is kind of a multi-layered Turing machine, a Turing machine whose job it is to read the instructions of another Turing machine and then carry out that process. And that is what the modern computer can do. So that's exactly what we want to do. Take a Turing machine that takes the input and description of another Turing machine and then says, I'm going to do what you do. How can we design a Turing machine that reads what another Turing machine does and then does that?
This is the mic drop moment of the class, isn't it? Where it's like, congratulations.
The rest of this class is going to just be nonstop shitting on your brain.
From my experience with assembly, you could define certain characters as being like opcodes. Some with operands, like go to this estate with this number, move this length, or move left or right on the tape. and so on.
Mhm. Okay, so it's starting to think kind of like assembly. I like it.
Then you just return to wherever you were, just like that. Got option.
So if we can theoretically argue that this universal Turing machine is possible, then that's interesting. So the process is really cool, but the results from this is that any Turing machine that we can envision has an associated binary string representation. So we can represent the associated states and transitions and input. So we take a machine's definition, that is just a binary encoding of the states and transitions, and a binary encoding of what's on the input. So we have a machine and we have an input, and we can feed both of these strings into a Turing machine that reads those instruction sets. Reads the states and transitions, reads the string, and then is capable of simulating what those states would do on that input. It's a pretty complicated process, but that is how this is done. We feed in both of those and we get a unique decoding of what that Turing machine is capable of doing. And since we know that a Turing machine can emulate some other Turing machine given a program, then we end up being able to simulate the instructions of that program on that Turing machine with the new Turing machine. And now we have an actual proper model of a modern computer. But it takes this level of kind of Turing machine recursion or Turing machine emulation. Use a Turing machine to emulate any other Turing machine string pair. And we have a Turing machine that is reprogrammable.
Once it can simulate itself, doesn't mean it's Turing complete.
Yes, that's the entire definition of where Turing complete comes from, is the Turing machine was the first Turing complete system.
Sense.
Turing was a freaking genius.
Yeah.
He did all of this before he died. What, 38, 40?
Yeah, before computers.
It's like my age.
When did you do that?
He committed suicide in his late 30s, early 40s, because of course, being gay back in the 40s and 50s was a heinous crime for which being one of the most renowned geniuses of the time does not make up for.
It was in like the 1950s, right?
Yeah,
He's like a war hero.
yeah.
From what I've heard, there's still debate over whether it was actually suicide or just accidental.
Yeah, that is fair. Regardless, it was persecution. And he was persecuted for that, which angers me to this day because I really wish that we had the rest of his life work. It probably could have put us forward 30, 40 years in terms of theoretical computer science. We would have invented the internet sooner. We would have invented, everything would have been, of course, there's pros and cons to that. Social media would have been around at our parents' age, and was the case. Maybe we're not around.
We would be saying 6, 7 right now.
Yeah.
Yeah.
Just check out Steve Jobs.
It's kind of.
He did all this before computers existed. Which is crazy.
Yeah. Yeah, before we really had more than Ada Lovelace's simulation.
Yeah. He wrote all this stuff. He's like, this is gonna be really important. Somebody trust me.
Yeah,
Crazy.
yeah, true genius. And yeah, cut way too short for how much he could have done from there.
Isn't that computer that you made in London in some museum?
Yeah,
Oh, man.
we're gonna take a quick aside for the moment and talk about something that will end up being very relevant as we talk further about Turing machines, and we'll see how much time for this we have, but let's just start with some examples. A set that is countable. What are some examples of countable sets?
Just anything that's a definite end, like, how many apples that you have, I guess.
Okay,
Like,
so-
something you can reach the end of.
Sure, something you can reach the end of.
Set of all integers.
Set of all integers, how do we know that that's countable? Actually, let's start with a set of positive integers.
Countably
It is countably infinite. How are we defining countably infinite?
discrete steps.
So there's a starting point and a way that says, given the current, generate the next.
Oh, that's yours.
Oh, it's induction. Which is funny, yeah.
I find the easiest way to understand countably infinite is by comparing it to something that's uncountable, for example, a set of all real numbers.
Yeah, we're gonna get there. That's a great point. So the set of all real numbers isn't necessarily countable, and we'll give some intuition for why that is. But how about the set of positive even integers? Is that countable? What about the set of all integers? What's the starting point of the set of all integers? We said as a way of talking about countably infinite, and everything up until the set of all integers has an obvious starting point. The set of positive integers, you start at 1, and the successor of 1 is 2. The successor of 2 is 3. Set of positive even integers, the first one is 2. The successor of 2 is 4. The successor of 4 is 6.
Start at 0. and-
Starting at 0?
But then you go 1, -1, 2.
Yes. So we're going to flip-flop back and forth between positive and negative, starting at 0, then you go 1, -1, 2, -2, 3, -3, 4, -4. And the idea is there is no integer that you would never reach with that process. You give me any integer, positive or negative, and I can tell you the number of steps that it would take. This algorithm that starts at 0 and just goes 1, -1, 2, -2, there's some number of steps that algorithm would take to reach that number. You could not give me a number where I say I can't get there, or this algorithm won't ever get there. Does that make sense? So because of that, it is countable. How about the set of all rational numbers? The rational numbers is any quotient, some integer divided by some other integer. Is that countable?
Say yes. Because it's made up of integers on the top and bottom.
Depends on how you do it. So how are you saying that we do that? So we could do something like 1/1, 1/2, 1/3, 1/4, 1/5. Will we ever hit 2/1? That's not saying it's impossible. Because it is possible. The question is just how. Now there are algorithmic ways to get it wrong, and there are algorithmic ways to get it right. Just like the set of all integers, if you start at 0 and just go up 1, 2, 3, 4, 5, 6, 7, you never get to -1. It depends on the algorithm you use. The question is just, is the algorithm impossible to generate? Or is there a way to generate such that for any rational number I give you, you tell me the number of steps that it will take for your process to generate it?
Can you do it like, sorry, you can-
I mean, you could do, I guess, like a breadth first search, so that you check it. So. But like, if you do like 1/2, and then you look at the next one, it's like, oh, I'm done with this layer, I'm gonna go to 1/3, 2/3, I'm done with this layer, and then keep going.
Same thing on that.
You can do it, sorry, no, it's
So good.
Yeah, so we do have to stop for the day, but for those of you for whom this is not readily apparent, what we would do, I will start tomorrow's class by drawing this out and making it intuitive.
See, I just read your brain. That's all I did. I just
I know I'm on the right track when you say one other thing. That's so funny.
Yeah, so I'll see you all for that tomorrow. I'll be in my office in an hour.
See,
We're office hours.
Yes.
Got it.